just put on the record. So without further ado, I present to you Noella. How about you start by giving a brief introduction to yourself, and then you can just take it over.
Yeah, don't worry. I have that in the slideshow. So
Nice.
that's okay. Can you all see my screen?
Yeah, we can.
Okay, perfect, perfect. Oops, hold on. Okay, so hi everyone. Today I'm just going to be doing a small, informal introduction onto computer fundamentals and specifically the important things that you'll need to know for coding. So first, I'll just give a little introduction to myself. So hi, I'm Noella, and I currently work as a software developer at UK Research and Innovation. So basically what I do is I help write the software for particle physics experiments. Now, as Simon mentioned, I don't actually have a degree in computer science. I have a background in biomedical engineering. And so in biomedical engineering, we work with a lot of electronics and sort of understand, I guess, the details of how computers and electricity works. And that's something that I found to be super, super helpful when I learned how to code. And I hope that's kind of what I can do today here for you. So right now, I guess for most of us, or at least how it was for me when I started, is when I coded, I just wrote a program, gave it to my computer, didn't really know what was happening. And then, like magic, the code gets run and everything. And this is fine for now. But I'm sure you will all find that you reach a point as a developer where things get a lot more complicated and it gets a lot harder to, I guess, code if you don't really know what's happening. And for example, in my work, I actually get errors like this a lot. And yes, it looks like a bunch of nonsense. And so if you don't know what's going on in your computer, it's going to be really, really hard to debug what this means. So first, I'd like to start by just defining what is a computer. So what is this thing right in front of you? It's a computer is defined as just a machine that can store data, process it, and execute instructions. So with these three simple principles in mind, a computer, it doesn't actually have to be electrical. It can even be mechanical. For example, this is an example what early computers look like. So this is a mechanical computer, and it does all those three things. It is technically a computer. It stores data, it processes it, and you can actually write code for it. But nowadays, computers are electrical, and they understand what's called binary. So you've probably heard of binary before. It is just zeros and ones. And this is all your computer in front of you understands. Now, each binary digit or bit actually corresponds to an element of hardware in your computer that has an off state, so no electricity or zero, and an on state, which has electricity and represents one. So the current number system that we use in our day-to-day uses base 10. So that means that when we have a number, we represent it from digits 0 to 9. And for every extra digit, it corresponds to an increasing power of 10. So 10 is actually 10 to the power of 1. And then if we add another digit, another 0, it becomes 10 to the power of 2. And then if we add another digit, it becomes 10 to the power of 3. And that's why it's called base 10. Now, with computers in binary, we use base 2. So we represent numbers with only two digits, 0 and 1. And as you can see in this table right here, I've sort of put the binary or base 2 and then the base 10 or our current number system representations. And you can see for every extra digit that we add in binary, it corresponds to an increasing power of 2. And so you may ask yourself, why are we doing this? Why do computers use binary when it is so much easier for us to understand 1, 2, 3, 4, 5, 6? Well, it really all boils down to physics and hardware limitations. So imagine that we're tasked with creating a calculator that can add two numbers. If we don't want to do this the binary way, what we can do is create an analog calculator and have two wires that join together. And through one wire, we can put 0.6 amps of current, and the other wire, we can put 1.2 amps of current. And then we can measure the resulting current, which is 1.8. So I guess to help illustrate this further, I have this little video showing that. So as you can see, we have one wire here, which has 0.6 amps of current, another wire here that has 1.2, and then out the other end, we can calculate that they add together to 1.8. Now, this all looks great and works great in theory, but in real life, you're actually going to get something like this. And that is because in the real world, electricity isn't consistent, it fluctuates. Wires have varying resistances and small little errors that we have to account for. And that means that our outputs are not going to be super accurate and precise. And that's not great for computers nowadays because when we want to do really complicated math, we need to make sure everything is super precise. And so with binary, instead of needing 10 different electrical states, where if you can imagine, like for the number two, if the electricity fluctuated a little bit between 3 and 1, and you couldn't really tell if it was 1, 2, or 3. With binary, we just need two states, off or on. And it doesn't matter if there are fluctuations in electricity because one will always be off and one will always be on. And so we use a combination of these on and off states to represent a value. So 0, 1, 0, 1 is equal to 5. And so that is why we use binary. So now with that in mind, I'm going to walk you through the different hardware elements of your computer. So we're going to start at one of the super important ones, which is your CPU, or central processing unit. And this is generally referred to as the brain of your computer and is actually where all your code is going to go. So the CPU, like every element in your computer, only speaks in binary. And so it understands what's called assembly code. So all of the instructions that the CPU executes is in assembly code or binary. So for example, 0001 represents loading a value. And then 0011 means add two values together. So just as an example, if we wanted to tell it to add 5 and 7, we have these instructions. And in this case, the instructions are made up of 8 bits or 8 binary digits. And the first half is going to be the instruction, and the second half is going to be the value. So for 5 and 7, we have 0001, which means load a value, and then the number 5 in binary, and then 0010, which is also load a value, but to a different location, and then the number 7. And then we have add 5 and 7, and then store the result. Now, these binary instructions are called opcodes, and in this case, they are 8 bits, which means that our CPU in this example is an 8-bit or an 8x CPU. And you might have seen this in software. When you're downloading software, sometimes it says x32 and x64, and that's all it means. So an x32 CPU is going to understand instructions that are 32 bits long, and a 64-bit CPU is going to understand instructions that are 64 bits long. So after going over the CPU, let's talk about another really key component of your computer, and that is your memory. So there are two different types of memory storage in your computer. You have the long-term storage and the short-term storage. So nowadays, for long-term storage, we typically use SSDs. or solid state drives. And back in the day, we used to use like CDs or hard drives, and they have the little spinny things. But now, most computers, like the one in front of you, is probably going to have an SSD, and they look a little bit like this. So, in your SSDs, you have these components called your NAND flash memory. And the technologies used vary from SSD to SSD, but what these components kind of look like is they're sort of a grid or an array of a bunch of little cells. So a bunch of little bits of silicon that either have electricity, aka they're the number one, or they don't have electricity, which is zero. So that's how your data is stored basically. And then we have our short-term storage. So our short-term storage is called the RAM, or random access memory. And you might ask yourself, why do we use RAM and SSDs? Because essentially they both do the same thing. They both just store bits. So why do we have both? Well, it's really down to the hardware limitations. So when we have long-term storage, we need to store a lot more data, but that also means that they're going to be a lot slower. Whereas with RAM, it typically stores a lot less, but is also a lot faster. So I like to think of it as kind of like a warehouse and a store. So in your warehouse, you can keep loads and loads of items, but it also means that it's super hard to go through and find the exact item you need. So then you have a storefront where you keep the items that you need readily available, and then it's a lot quicker to find everything. And so this is how your RAM typically looks. It basically stores data in a bunch of, I like to think of them as lockers. And each locker has 8 shelves, which are capable of storing 1 bit. So with 8 bits, you have 1 byte. And then each locker is numbered and named. But in our computers, they're not really named locker one, locker two, or locker three. Instead, it's a bit like this. And so these are called memory addresses. And in programming, when data is passed around, your computer doesn't actually pass around the data itself, but instead passes around its memory address. And this is commonly referred to as pass by reference, and you'll probably see it come up. And now you might think, hey, those memory addresses look a little bit familiar. Well, let me just show you back to the error message that I put earlier in the presentation. So now that we know a bit about computers, let's actually see what this means. So as you can see over here, you have a list of a bunch of different memory addresses. And then over here is actually the assembly code, or the CPU language, as we saw earlier. So right here is where the code failed. And it failed at this memory address with this instruction, which is essentially telling the CPU to load a value from address. So now seeing that, I can see that what happened was that the CPU tried to load a value that it couldn't have access to. Or if we think back to the locker analogy, I tried to give the CPU a locker that was locked. And so basically what happened in my code is that I didn't properly initialize a variable, and that caused it to crash. And so basically we know by now that all our CPU understands is assembly code. So basically all the code that you write gets translated into this assembly code. And we can actually code entire programs just with assembly code. And in fact, that has been done already. So there is this very famous game. It's called Roller Coaster Tycoon. And it is entirely written in CPU assembly language. But can you imagine writing a program like this? It's not very intuitive. It's very hard to debug and understand. And so that is exactly why we have programming languages. So your programming languages are just a way for human and machine to speak to each other. And something that's super key to understand is that the programming languages are not there for the machine, they're here for the human. Because the computer is perfectly fine speaking in binary, but we really struggle with that. And that's exactly why we have programming languages. So there are two key types of programming languages. You have your compiled languages and you have your interpreted languages. And now, what compilers and interpreters are, they're both very similar, and they are essentially just the translation units that convert human code to the machine opcodes that your CPU understands. So the difference is compilers, they translate the whole code ahead of time. So they'll take the code that you write and then translate the entire thing into machine code, and then it'll get executed. Whereas interpreters translate and execute the code line by line. So you can imagine, I guess, if I was speaking to someone who only understood Japanese and we had a Japanese interpreter, I would say a sentence and then the interpreter would translate it into Japanese with every sentence that I say. And so the difference is compiled languages have much faster execution. And that's because the whole thing is translated at the beginning. So it's just ready for the CPU to execute. They do require more memory because the whole program has to be stored in your RAM. And it is a little bit harder for the users to code. So these are languages like C, C++, and Java, and you will probably hear them referred to as low-level languages. And that just means that, I guess, they are closer to machine code. And then you have your interpreted languages, and these are a bit slower to execute since everything happens line by line. And they require less memory since you only need each step to be stored in memory at a time. Now, these are a little bit easier for the user, and these would be languages such as Python and JavaScript. So we've covered a bit of the hardware, and now I'd like to do a little quiz. So it's up to you if you want to put your responses in chat, but you can also just, I guess, choose your answer and see if you got it right. So the first question is, what does RAM stand for? Now I'll just give you a couple seconds to think to yourself before I show the answer. So the answer is C, random access memory. And our next question is, what does an x64 software mean? So I'll also give that a moment. And the answer for that one is B. So x64, if you remember, it just means that the CPU understands instructions that are 64 bits long. So x64 software is just software that has been translated into these 64-bit instructions. And now for the third question, what feature is not found in a compiled language? And the answer is B. So compiled languages, the entire thing is compiled beforehand, and the ones that execute line by line are interpreted languages. Okay, so now on to the next section. Just give me a moment. Well done for everybody who got the answers correct. So the next section is going to be on operating systems. So this is another very key part of your computer. And an operating system is basically like Windows, Mac OS, or Linux. Okay, so I just got a question. Would you kindly repeat that part for 32 and 64-bit? Of course. So I'll just go back to 1 second. I'll just go back to this slide. So basically, the CPUs understand instructions in binary. And so if we use an example of a CPU that is 8-bit, it understands instructions that are just 8 bits long. So in this case, we have the opcode, which is um, either load, add, store, and then the value. So for example, this means load 5. And because we use 8 bits per instruction, the CPU or the software we write for it is called 8-bit. But then if we have x32, it means that every instruction is 32 bits long. And that just means essentially that the CPU is capable of doing more complicated things because with only limiting ourselves to 8 bits, there's a lot less variety in commands that we can give. Okay, back to operating systems. Okay, so I like to think of your operating system as kind of the train conductor between software and hardware. So your operating system has to do these three key things. One is provide a user interface, so either command line or graphical. GUI stands for graphical user interface, and that's what you're looking at right now on your computer. And it also has to handle the launch and the management of every application. So if we see the operating system placement in your computer, it sort of goes between the hardware and the application. And basically, the operating system allocates different resources to each application. For example, like dedicating RAM for certain applications, and also just dealing with errors and all of the tasks that your computer needs. And another key thing is that your operating system has to manage your file system. And in your computer, all of the data that you have, everything is stored in your file system. And this is something that I think is super great to just think about. But everything in your computer, all your data that is in your long-term storage is represented and accessed in a file. And that's just like, I guess, your Word document, your PDF, those are files, just like all your code files are. And so, what is a file really? Well, a file is basically just a set of bytes or bits that are used to store data. And so, every file contains metadata that describes the file type and how the bytes should be read. Because essentially, an image file and a text file, if you open up, they are all binary and they all look the same. So we actually have to tell the operating system and the applications how to read that file. So for an image, you'd have to read all the binary and take them and turn them into pixels that you can create for an image. And then for text files, you'd have to take all that binary and turn it into letters and words and everything. And so the code that you write is also just organized in different files and folders. And it is no different to the standard applications, which are also just a bundle of code files. Zoom right now that you're looking at is also just files. And I guess there's no magic, there's nothing really special. Everything is just files and binary. And so knowing all of these things, let's look at, I guess, what I like to think of when I think of a modern computer. So, if you remember our definition of a computer, it has to store data, process it, and execute instructions. So, a modern computer is sort of all these elements working together. It has all the hardware, and then it has your file system or all your data. And then you have your operating system that sort of manages the two. So now, knowing all that we know about computers, Let's follow the journey of your code. So step one, we write our code file. So this is just a file like any other, and I'm just using an application, Visual Studio Code, to edit all of the to edit and write all the code. The second step is our code file is saved. So we save the code file and it's stored in our SSDs, if you remember the long-term storage, and it's stored in a bunch of zeros and ones in one of these NAND flash memory sections. Now, the third step, where the magic happens, is running the code. So what actually happens is that your code in your human readable programming language like JavaScript is loaded from the SSD, and then you have your compiler, which is also just a code program that sits in the RAM, and it takes the human code and it translates it into machine code. And this all happens and is stored in the RAM. Then all of this machine code is given to the CPU where it then gets executed. And this whole process is managed by your operating system. So now that we've covered all of this, I think that it's super important to go over, I guess, another key feature or thing that you will probably interact with a lot when you're programming. And that is the super scary terminal, which I promise is not that scary at all. I remember when I first started coding, I had no idea what this thing actually did. And because, you see in movies, you see hackers, they pull up the terminal and then they start typing commands and hack into the government. And I was always super scared of it. And the only things I did, sorry, I just got a question. What if the language is interpreted? Does it go through the compiler? So this example right here was actually for a compiled language. So in this case, all of the code gets compiled beforehand into machine code and then given to the CPU. With a interpreted language, it's still very similar. The interpreter sits in the RAM, but instead of it all at once being transformed into machine code, everything just happens line by line. So the interpreter will sit in the RAM and it'll take your code, translate that line into machine code, give it to the CPU, let that execute, and then that process will repeat for all the other lines. In the next slides, we'll go into that a little bit more because I'll do an example with JavaScript, which is interpreted. Kind of like a loop. Okay, so another question
Yeah.
for languages. For languages like C, are there many alternative compilers that are more or less efficient slash fast? Yeah, I guess for C and C++, you can use, because essentially compilers are just pre-written programs. Somebody wrote them and defined how the code gets transformed into machine code. So for C or C++, which is another type of programming language, there are different compilers like GCC. That's the one that I personally use. And they're all, I guess, pretty similar in the efficiency or the speed. But it is really up to you what compiler you use. And so back to the terminal. You might ask, why do we use it? Why do we use the terminal? Well, basically, it is a text-based interface to your computer. So it's the same thing as what you're looking at on your screen, but just a lot less pretty. And this time, instead of taking your mouse and clicking and doing all the things that you do with your keyboard and your mouse, instead you type in commands that get executed by your operating system. So instead of clicking a button, you'd type a command that does a similar same thing. So the reason we use the terminal is because it is much more efficient. Sorry about the background noise. Um, we use the terminal because it is a lot more efficient and it lets us automate tasks. So if you were using the graphical interface, in order to automate it, you might need a little robot that goes around and clicks or types for you. But with the terminal, we can just give it a script and a list of commands, and then our operating system can do all the work. So I'm going to go through the terminal a little bit, and you can choose to follow along if you wish. So if you are on Windows, on the bottom left, you can search up CMD, and then that should let you open command prompt. Now, you can also just watch the examples that I put on. So I'll just give you all a moment if you decide to open the terminal. Also, feel free to put any questions if you have them. So my terminal, I'm on a Mac, so it might look a bit different depending on the operating system, but essentially they all look and do very similar things. So in our terminal right here, you'll have a little section over here, and that tells you where you are in your file system. And this is also called the current working directory. And so it usually is always going to begin at your root directory. Yes, so PowerShell, so in Windows, you have PowerShell and you have command prompt. Yes, I can start again. So with Windows, you have PowerShell and you have command prompt, and they basically do the same thing. However, PowerShell, the reason that they introduced it is because it offers a bit more security and is a bit more restrictive than, I guess, the traditional command prompt. And between the different commands or terminals that you're using, the commands that you give it might vary just a little bit. But okay, just starting again. So you can open your command prompt just like this. And then basically over here, what it'll show you is it'll show you your current working directory, which is where you are in your file system. And it usually will begin at your root directory. So just your main folder in your computer. And now let's try giving our operating system a few commands. So what you can do is cd, which stands for change directory. And if we do cd documents, we're just saying go to your documents folder. So if you notice in the current working directory, we can only access the folders that are present in there. For example, if I try to do change directory unicorn, it wouldn't let me go into it because there's no folder in that directory called unicorn. So then now that I'm in my documents folder, which is my working directory, I can do the command ls, and in Windows, it's going to be dir. So if you just type out dir or ls, depending on whether you're on Linux or Mac or Windows, it'll give you a list of all of the file system objects in that folder. So over here, I have some screenshots, some PDF files, and then applications and different folders. And so just to, I guess, give a more background into the terminal, I'm going to go over a terminal tool that you all will probably have to use at some point. And this is the package manager. So just a little background onto the package manager. A lot of the times when we code, we actually use code that is already written, so we don't have to rewrite it. So these are libraries like React or Tailwind, and it is all just pre-written code that we can use to make our lives easier. And in your code projects, these are going to be referred to as your dependencies, also known as the code that your code depends on. And that's where dependencies comes from. And so when you code to make the managing of these dependencies easier, you will often use a package manager. So if you're coding with JavaScript, you'll usually use npm or node package manager. And then if you code on Python, you'll use pip. And a package manager just automates the process of installing all these dependencies so that we don't have to go and do it ourselves. And I would like you all to remember there is no magic with computers, and you have to tell them where everything is. So the package managers just help you tell your computer exactly where all the code you need is. And so if we do a terminal example using npm, now this will only work if you have npm installed. So if we do mkdir example, that means create a directory called example, and then we change directory into example, and then we call npm init -y. And all this is going to do is create a package.json file that is going to contain a list of all of the dependencies that we are using in the project. And so if we see this little command, npm, all this is a predefined variable in our computer that predefines the word npm to point to a program on our computer. So we can actually see where npm is if we do the command npm root -g. It's going to tell you where the folder is located for npm. And in my case, it's in user local lib. And so we can go over to that folder, and then we can see the actual npm program that is being run. And so just to test that it all works, we can run the exact same command that we did before, which is npm init -y. But instead of giving it the command, sorry, just a question came up. I have more questions. I will put in my email at the end if anyone wants to email me and ask me more questions, so don't worry. But instead of saying npm init -y, we can actually give it the script or the code file that npm is on, which is this right here. And then we can call that same command, and it's going to do exactly the same thing. So if we actually look inside the npm file, you can see that it's code just like the code that you write, even with comments from the developers and everything. So I guess I showed this example because I really want to show to you that your applications and everything you do on your computer is all just code, and it's all just files, and there's nothing special. Like, there is no magic. And so for the web, when we execute code, it's a little bit different to how we do it in, for example, in Python or C++. So when we code for the web, there is a key application that we are using, and that is your browser. So this is like Firefox, Internet Explorer, or Chrome. And a browser is essentially an application that is used to display content from the web. So your browser is just a program like any other, but it has a predefined set of rules, so HTML or CSS, which tells it how to generate content. So basically, you have to tell the browser how to make all these pretty pictures and render all the web pages. And so when you code for the web, you're not really coding for a machine, but you're coding for the browser. And so, just like we did before, let's go step by step in how your code is executed for the web. So the first step is when you open a website, the browser is going to download code from the cloud. And I used to think that the cloud was just this magical thing. And I was really sad to learn that the cloud is just a room of computers, just like what you have in front of you. Basically, everything on the web is stored in some physical hard drive somewhere in the world. So every web page, everything, it's going to be in an SSD somewhere in the world. And so when we go to a web page, we're going to download code from the SSD living in the cloud. And then we are going to get that code, and then it's going to go into the RAM again, where the interpreter is going to take that JavaScript code and translate it line by line into machine code for the CPU. And this whole process is managed by the browser. And as you can see with JavaScript, there's a little bit extra things. So JavaScript is run with what is called the JavaScript runtime. And this is just sort of a set of programs and different things to help run the JavaScript code. So with your JavaScript runtime, you have the garbage collector, which helps manage the memory in the RAM and make sure to clear and create memory. And then you also have access to the web page data. So your JavaScript understands all the HTML and CSS that's on your page. And so everything, all of this is managed by the browser, but everything is also managed and policed by the operating system. So that hasn't changed. Okay, so I'll just give everyone a moment to process this. And before we finish up, it's time for one last quiz. So the first question, feel free to put your answers in the chat, is why do computers use binary? Now the answer is C. So good job to everybody who got it correct. So I noticed that a lot of people said A, and that is still correct, but B is also correct as well. Now the next question is when your code is being executed and run, where is the translated machine code stored? Is it stored in the CPU, the SSD, or the RAM? Now the answer is C. I noticed that some of you put A, which is somewhat correct because the CPU does, I guess, executed all of these steps, but really all your machine code is being stored on the RAM where then the CPU is going to grab that code. And the third question is what is the difference between a text file and an image file? And yes, the answer is B. So good job to everybody who got that correct. So just to recap, all files are just collections of binary, but in a file, you have metadata, which tells your computer how to translate it. So for image files, you translate all the binary into pixels, and for a text file, you translate it all into letters. So I hope I helped clear up some of the confusion or the mystery behind computers. And hopefully, it's not going to be all magic anymore. So, thank you all so much for listening. If you have any questions, feel free to ask them.
Okay, thank you, Noella. That was great. I think
No
I've
worries.
never really had an introduction to computers. I also appreciate that as a non-developer, sometimes coder of Python.
Thank
Um,
you. I'm so glad you enjoyed. Yeah, I think it's because when I first started, everything just seemed like magic. But then I realized that computers are actually a little bit dumb and we have to tell them everything. So,
yeah, definitely, definitely. Especially the part of like managing packages and like telling people where things are, or like telling the computer, or like here's where I have everything and here are the packages. Ah, that was a bit of a uphill.
yeah,
Um,
I
okay.
just put my email in the chat if ever anyone wants to ask me questions, feel free.
And so people say that like Python is kind of slow.
Yeah.
Is because they do it line by line, but like are there other things that make certain languages like slower or faster?
Yeah, I mean, it's a bunch of different things. So, as you can see with JavaScript, there was a lot more components in the JavaScript runtime, which means it's a bit more complicated to run. And what you see with programming languages is typically the easier it is for you, the programmer, to use,
Mhm.
the more slower it takes for the computer to run. Because the closer the code is to machine code, the faster it is to execute. And so with Python, there are a lot of little details like, for example, you define code using indents and all of these rules that sort of, it makes it a lot easier for you. But then in the interpretation of the code, you have to do a lot of extra steps just to check and make sure everything.
Right. I remember in Java, you had to do like semicolon after every line or something like that. No,
Yeah.
that's like so annoying. And then you get errors and you're like, you just missed the semicolon somewhere.
Exactly. That's exactly how it is with C++. But that's what lets it be so fast. So C++ and Rust are really fast languages. And that's just because you have to do a lot of extra work, like add semicolons so that the computer doesn't have to figure that out. Okay, I just got a few questions, if it's okay if I could just go through them. So, one question is in high school, we were taught to convert numbers to binary codes. Will we use that here or will the computer do that? So, the computer does do that for you. So typically, when you code, you'll define a variable and you'll tell the computer what type it is. For example, if you're defining a number, you will use like int or integer, and then you will give it a number. And that just tells your computer, oh, we need to translate this into a binary code that corresponds to a number. So you will never really have to touch binary. Oh yeah, also don't forget to fill out the feedback form. I have never had to code binary or convert numbers into binary. Your computer does all that for you. Um, and in fact, the compiler or your interpreter will do that all for you. And so, will English become the new programming language? I mean, technically, it already kind of is because C++, JavaScript, they all do use English. But actually, depending on your region, you can actually code in different languages. So some people code in programming languages that are translated to Russian, for example. So instead of like writing um, for in English in your code, you'd write, I guess, the Russian or the other language equivalent. And then somebody else asked, what is an opcode? So if we just go back here, sorry, it's a bit far. Yeah, an opcode is basically just the instructions that the CPU understands. So it's just CPU instructions, basically. So 0011 just is an opcode, which is an instruction that tells the CPU to add two numbers. Okay, so should we just give everyone 2 minutes for the feedback form?
Yep, sounds good. Right now we have two people who have submitted the form, and we want
Come on, everyone.
yeah, let's get to it. Let's get to the last. And my actually speaking of the CPU, my grandpa actually built like a physical computer when he was young.
Wow.
I'm like, wow, that's cool. So when he was, I think he was like 18, 19, like first, second year of university, that's what he did for fun. Like he built like computers, which I thought was super cool.
Yeah, exactly. No, that is so cool. I'm always interested. Well, I'd love to, for example, in early computers or when they're trying to build computers, they use like pressure valves, or even in ancient times to do computation, they use like water streams and
Mhm.
like water currents. So it would be super fun to try and make something like that someday. Um, Two more questions. NVIDIA CEO stated that AI will possibly make coding for everyone. What does that mean for the future of programming? So I feel like both me and Simon can kind of answer this question. Um, I would say for now, it's not that good at all. Like I do use ChatGPT sometimes just to, for example, if I have a huge bit of code and I'm trying to find out where an error is, I will just let ChatGPT do it, but it's not good enough to replace a human, and it probably won't be for a long, long time. And at the end of the day, the AI needs someone to give it instructions and to put all the code that it does into, I guess, programs and put it all together, basically. So it's, as somebody who works in software development, AI is a long, long way from ever replacing people.
Yeah, and just to add to that, I would say that one of the reasons why we emphasize now, especially more of the soft skills, like I mean, working together in teams and like problem solving and entrepreneurship, is because you need to be able to like solve problems and like identify what needs to be solved and what's important and so on and so forth. And then what's going to happen is I don't think we're going to introduce it too early, but we'll introduce various AI tools that you can use to become just faster at doing whatever you wanted to do. So more than anything, it's just going to be make life slightly easier. And I mean, when me and Noella learned coding, ChatGPT wasn't the thing. It is so much easier to learn things now with AI because you guys can like just paste a piece of code and say like, oh, what's wrong? Like, what is the bug here? Or please explain this like thing to me in like I'm 5, and then it just does it.
Yeah, exactly. I feel
Mhm.
like with AI, it doesn't close jobs, but it creates new ones. You know, for example, like you can do with AI, it just helps you code a lot more things a lot faster. So if anything, it helps all of you as developers. And somebody asked, how do people in other countries code with other languages like Chinese? Well, basically, just like how we do it in English, but all the letters are going to be in Chinese. So it's actually a lot similar, but usually people in other countries prefer to code in the English version of programming languages just because it's a lot easier to find help and resources out there.
And also to clarify, for the feedback form, this is for today, for Noella. It's not for Saturday launch day. Just keep that in mind. I saw one at least that was about from Saturday. So keep that in mind. We actually didn't send out the feedback form for Saturday, which is a bit bad. We'll yeah, we'll just ask for that at some other points probably.
Um,
Got 22 submissions. Come on, let's get 20 more at least.
yeah, come on, guys, you can do this.
Yeah. Noella's
Um,
worked so hard to prepare for this, so I feel like you should at least fill in.
so somebody asked me, why did you specialize in what you do?
Oh, I'm gonna mute Alan, I think. Let me see, Alan. Mute you.
So basically, I'm sort of working in this field for a year. And I chose to work. Basically, in university, we had the option to do a year in industry. So I decided to do a year in industry in something more fun. So particle physics and um, neutron scattering. Because if I was going to work for a year and I could choose anything, then I wanted to choose something really fun. Um, but really, I usually just like outside of coding for my job, I like to do, just web development, application development, and other things. And thank you, everyone, for the nice comments. I really appreciate it. It's my DM, so you won't see. But
Okay, we got 37 completion. That's great. That's great. Um, I'll say a few things that would like some. Well, I'll send it to you, Noella, actually afterwards. You can have a look at the feedback. Um, but overall, very positive. Very positive.
yay!
Some people, well, someone had challenging with unstable internet. Um, but other than that, pretty okay. Pretty okay.
Okay, I also got a question, which is what would be your advice to us who are just beginning this journey? I'd definitely say just stick to it and make sure you do a lot of projects for yourself. So, for me, especially since I didn't have a computer science background, the only thing that I could, I guess, give when I'm um, like applying for jobs or whatever is showing, I guess, my passion and my personal projects. And a lot of the time, you can prove your passion through your own personal projects. So what I did was just, I guess, if I had a problem, like for example, if something that I did was a random password generator application, so because I like to use randomly generated passwords, I was like, let's turn that into a coding project. And if you just do a bunch of these little small projects, you'll end up learning a lot. And it also shows, it's a good way to show experience without having, I guess, a computer science degree or a work experience. And I started learning how to code in 2020, so over quarantine. Thank you so much, Abigail, for the kind words. I really appreciate it. Simon, how's it going on the feedback forms?
Um, it's going quite well. I'm just trying to clarify in our instructions a bit because some people gave feedback on like today's content overall, which I mean I understand it's not super clear. So just edited that. But feedback numbers. Let's see. Check that. Submissions. We have 45. Okay, they're still coming in. Still coming in. Someone said you can feel the passion of the teacher.
Yes, I love computers a lot. So.
Yeah, no, that's true. That's true. Someone said add more time for Noella to talk to us. So maybe they want you back. Oh.
Yay! Thank you
Um,
guys.
Someone said Noella was very engaging, 10 out of 10 host.
Yay!
Um, yeah, yeah. I mean, there's a lot of like a lot of very good, yeah, good feedback.
I'm really glad you all understand computers a bit more.
Yeah, yeah. Some were confused by certain new terms. I think
Mhm.
that's definitely very easy to like, take certain things for granted. Um, yeah, the quizzes people like. Next time, I think we're gonna add some recommendation for the workshop lecturers. Yes, and yes, you may leave now. It's already five past, 5 minutes past. So
Yeah.
yeah,
Thank you all. Thank you all for joining. Um, would you,
I'll just pause the recording.